This is our embedded system design project, which we have done and submitted as a part of our course in embedded system design at CDAC Bangalore. The title of our project is IoT smartwatch prototype based on ESP32 and FreeRTOS. So the idea is we are trying to do a prototype of the general smartwatches which we have and which are in the market, but we are trying to get it and show it how we can implement it using FreeRTOS. And for that we have used an ESP32 dual core processor. Now I'll just do it in brief so that you can understand how exactly this project is. So initially we have written the code for the smartwatch project, and we have written it such that we have not implemented the RTC clock for the project, but rather we have implemented a software RTC. The reason for that was we wanted to demonstrate the capability of our program to stop all other RTOS tasks at boot time and wait until the user actually gives the time, sets the time, and then the control goes back to the other FreeRTOS tasks. So right now I have already flashed the program, and I'll be opening the terminal, and as you can see, serial monitor. As you can see, this is a serial monitor, and here once I reset the flashed code, it gives me an option to enter the date and time, and it has to be entered in the same format. So 2026 January 22nd Thursday, and what is the time right now? It's 18:54. So we just set the time 18:54, and let's say 59 seconds, enter. And the moment I've entered it, the code has started, and as you can see, the display has turned on. Previously, if you did notice, the display was turned off and all these tasks were not available. Right now, let's go and introduce the smartwatch to you. This is our smartwatch display, which is an OLED display based on S1106 driver. Then we have our three buttons for controlling our smartwatch: the home button, the right page, and the previous page, the next page and the previous page. So as you can see, we'll go to the next page. In the next page, it's just a simple hello OLED task which gives an introductory task, just to show that the tasks are not fighting with each other for the OLED resource. So we'll go to the next page. The next page, I had given the screen for showing how many digits are possible on this OLED display. As you can see, it gives you 20 digits by 5 digits in this one. If you change the fonts, of course it can vary the number of digits, but this seemed ideal, so I left it at this. And another thing, if you notice, the LED glows. So this LED glowing was used to demonstrate that this LED task is synchronized only with this particular screen task. So if I change the screen to any other task, the LED stops glowing. So I wanted to use it to demonstrate that two tasks can actually sync with each other without causing any disturbance. Now coming to the previous page, if you want, I'll show you the working of the previous button. So as you can see, the previous is also working. And at any point in time, if I want to go back to the home page, I can go to the home page. Now, the another sensor which we have implemented as a part of our project was the EMU sensor. The EMU sensor is something which actually takes the readings of the movement based on accelerometer and gyroscope. And based on that, now I'll take you down to the accelerometer readings, which you had already seen earlier on the screen. We have also got it to display on the OLED display. As you can see, AX, AY, AZ, as we keep accelerating our EMU sensor, it keeps changing, the readings keep changing. Similarly with our gyroscope readings, as you keep changing the orientation, the readings completely keep changing. Now, once we get this part of our sensor working, all these are actually connected via I2C communication, serial communication. So we have accomplished, as you can see, a single I2C bus. We have added two external nodes. Now let me continue and show you the other screens. Now this is the application of what we have done for our this is the application we have done for using our EMU sensor. The idea is, if the user is sitting for a period of 1 minute, it will ask the user to stand up. Now let this continue, and let's move on to the next screen. One thing you'll notice is this counter keeps going on even when we are on other screens. Now coming to the next screen, here we have actually implemented a dial. The dial is, it's another simple way to explain the use of the dial is, take the case of flights or aeroplanes. Generally, when pilots are actually flying around, they won't be reading the accelerometer readings and then adjusting the level of the flight or what the flight is doing, the orientation or or if they want to rise up, and other such readings. They will have other such dials such as altimeter and GPS to navigate. But this is also one part. This sensor actually plays a key role in their navigation systems. Now let's go to the previous screen and let's see whether we have got a notification. As you can see, the EMU sensor has not moved, and we still got a notification. One nice thing we implemented in that is, if we just if there is any noise below 2 seconds, it won't register. See, okay, this one got moved. The moment I made a movement, it went back to 0. So even when the notification also to stand up left. Now we also implemented that even if we make small movements, it won't register, but this count still keeps going on. This is to avoid human errors, so we can code that also into the system. Now coming back to our dial, if you see, this is how the best use case will be in navigational systems. This is the most common use case. So let's say the flight is taking off, so we know what is the acceleration is taking off, and then when he wants to level up, as you can see, the central disk, it's leveling out. Or in case of a sudden gust of wind, if it's flowing this way, then he'll adjust his control so that he can come back to the center again and maintain a normal orientation. So as you can see, this is quite frequently used in flights also. And these days, this EMU sensor is vastly used in SLAM navigation, mapping systems, and various other systems. So this is one of the key sensors which we have implemented. Now coming back to the idea of our overall project purpose, we actually plan to further extend this idea. Now these readings, we plan to send these readings to the cloud via MQTT protocol, communication protocol. In that, the idea is, from the cloud, all this analysis, that stand-up analysis and all that, we can actually do that in the cloud. And now this can actually become a good smartwatch, for example, in the case of patients or other such users who are interested in health conscious activities. That processing can be done using machine learning or other such things. Once we can send this data via MQTT, we publish it. This ESP32 processor is a Wi-Fi Bluetooth module processor. Hence, we can use this generated readings. We can send it via MQTT, and we send it to the cloud or to a local device. And in the local device, we actually log these along with the timestamp, and then maintain logs. So for example, over a period of 1 month, we can understand the user's walking patterns, like when all did he go for a walk, or their sleeping patterns, or any other health related patterns. Or we can also generate, from the cloud, if we publish, if a user has suddenly fallen down, and we can publish an alert that the user is not moving when he's supposed to be moving. So it could be a case that he's having a medical emergency. Through machine learning, we can actually analyze that part. And the cloud itself can publish the alerts, which the ESP32, the moment the alert is published, can subscribe and sound a louder alarm and send notifications to all other related concerned people. And hence it can actually be proactive in maintaining good health and other such activities. Like even for sports related stuff, it is very useful. Thank you.
Look, start. Okay, so as Shiva mentioned that we are doing a smartwatch prototype based on ESP and FreeRTOS. My part is to connect these things to various things. So first of the major things that I want to tell, there are various AWS services. We specifically chose AWS IoT Core because it is very energy efficient and it is very resource efficient also. At the same time, I used IoT Core for creating basic tasks, basic IoT things, and so we can create multiple things in IoT Core. Like I can create my Windows PC for testing purpose. I also created my Windows PC as a Internet of Thing, and then we also created this ESP32 board as a Internet of Thing also. So how we are going to implement that? We are going to do that from IoT Core, and then I connected those things through Mosquito, and I'm sending whatever data I want, and I'm collecting all that data in the DynamoDB, and then I'm going to manage all of this on dashboard made through watch cloud. So let's continue with IoT core. So currently I have set it my I have made my current region as Asia Pacific South 1, which is Mumbai. Console awsamazon.com. Here we can manage and create new things. We can create new things, but for our purposes we'll straight away go to all devices and then we'll go to things. And as you can see, I created one Windows client and I created one MQTT client. MQTT client for ESP32 gateway and Windows 11 client. So they'll while they are loading, let me just tell you, after creating clients we'll get Amazon itself will give us the authority to give attributes, and we can customize them in a lot of manners. After that we need to go to, after creating things, we need to go to security, and from security we need to go into certificates. While creating things we also create policies, but I'm going to skip that for video purpose, and we'll directly go into certificates. And according to my policy, Windows 11 client policy, my Windows 11 client policy, I have created a certificate, asked AWS to create a certificate, and we can download the certificate from here. And after downloading, the certificates will look like this. The certificates will look like this. It will be a root certificate, and there will be a client certificate, then there is private key and public key, and my client policy, which will include everything for me to create a sustainable, good MQTT connection which is secure. So I'll just straight away take you through all of that, and I'll take you directly to codes for AWS Web Services. So our codes will look like this. So we are publishing things from Mosquito publish, and we have our header, and then we have to mention the whole header. Usually when we are doing locally, we are going with 192.168 IP addresses, and this thing we call it end of the device. So end of the device links are this, which we link with port, and then we need to add all the certificates here in the command itself. Every single time we need to add all the address and the command and the certificates. It will have my root certificate, it will have my client certificate, it will have my client private key, and then I will need to create a test subject, a test. So I just created a regular topic test, SDK test Python, and I sent message hello AWS. And after I'll send the message, I can also subscribe to the same Mosquito, and for subscribing also I'll need to have all these certificates to make sure that the server is secure. And this is the only way that Amazon will let us do with this. So we'll get all these things: hello Python, Python hello AWS, Python hello AWS. And if we go back now to dashboard of Amazon, it will look like this. So this is my MQTT test client, and here I again gave the same topic, and in the same topic we can publish messages from Amazon, which will look like this in the receiving area. And this is the bottom one, which you can say hello AWS, this one is from the Windows terminal that I sent. As you can see, it is plain text, it is not in the JSON format, but we can convert that in JSON format also. For that, we'll need to go with other tools. Let me just show you. So we'll go into terminal, and the JSON files will look like this. Because Windows terminal has issue with curly braces, we cannot send file directly in JSON format. So instead what we do is we create a JSON file which I aptly named log.json, and we'll send it with -f as a file, and as soon as we send the file, we'll get the certificate here. And if we go back again to MQTT, it will show that it received the file, like here as it is showing. It will show in this format, JSON format. So like this, we can collect all the data through MQTT from our IoT code. We'll receive all the MQTT files, and it will be stored in our DynamoDB. So I created a plain DynamoDB table, and the table will separate the thing in 3 parts, which will be, it will identify what is that message, it will identify who sent the message, and it will identify what is the topic, and then it will identify what's the time. So it will keep track of all the 4 things. And as we go from here to tables, you can see our mosquito logs, and we can, as we scroll down, our logs will appear here, and as our logs appear, it will keep on growing. And for final touches, we'll go to our CloudWatch dashboard. In CloudWatch, you can create multiple type of dashboards. For our use case, as you can see, we can create multiple kind of, but because we are using so less resources, those dashboards look almost empty. So because I send data in discrete chunks, it is looking like this, our current dashboard, which is a line graph basically, which is looking like this because it is a line graph basically. Idea was to basically send the data continuously from ESP32, the IMU sensor data, and both the values, accelerometer values and gyroscope values. So we can create a long log of the data, and we can train our ML models, which was our future scope. So we can train ML models on how the person is walking, or if the person is walking, or person is running, or person is resting. So we can identify all those things just from basic things, like after receiving data from our database, we can train our ML model on IoT also, because we can choose low resource versions like Edge AI models. So that will be all from my side.
I have actually, if you can see, I have actually started running Mosquito program on this, and at present, like, it has been, it's trying MQTT connection. The idea is on the local files, alright. As you can see, the network was not there earlier, but coming back to our MQTT, if you can see, I have already flashed the MQTT program on this. We have not yet integrated MQTT with the other EMU sensor data, but I'll just show you the working of MQTT. So what the idea is, we are right now publishing on the serial monitor. This is our program for MQTT, and we are having two topics. The ESP processor is publishing data via this topic ESP32 send, and it's subscribing to the topic ESP32 receive. The idea is we are communicating between ESP32 and this laptop. So we will, whatever message ESP32, which is publishing message, we are keeping a count of it. And as you can see, every 4 to 5 seconds, it's publishing a new message. That is being received on the local laptop in the monitor. This is the receive subscription. If you can see, I'll close this. I'll close the other one. This is the subscriber. I'll close it and I'll resubscribe. And as you can see, the subscriptions will start every 4 seconds. And then we can use, the idea behind that was to use the numbers as timestamps. And based on the timestamps, we created a database. And in that database, right now here we are only using numbers, but these numbers could actually be timestamps, and that hello from ESP32 could be the emu log data. So based on that, we can create monthly logs or weekly logs. We can create analysis from that, like earlier we showed in the dashboards. Now in the same way, let's assume this is AWS. Once AWS, we analyze it, we can publish from AWS. For example, here we are publishing hello from DASD CDAC. So we publish it, and then as you can see, the message arrived on the ESP32. So ESP32 can use this and display any alerts or anything. So there is actually communication going on between ESP32 and my local laptop here, which could actually be the cloud. We just need to integrate the AWS, which was shown earlier, and these same things can actually be accomplished via cloud. Here we are publishing new messages, and we are at the same time receiving. For example, hello, all the best to the viewer, all the best. Hello, or best of luck. We can give a new message, best of luck, and it will get published. If you can see, the ESP32 receive the message, best of luck, and then it continues to publish messages. These published messages are continuously happening, like they're simulating the sensors. The sensor data is being published and received online. So this is how MQTT we are planning to implement. This is the end of our project demonstration. I hope you all enjoyed the video. Thanking you all once again. We take your leave. Thank you.